Good morning, everyone. We are Group 10 here to discuss our feasibility study on solar hydrogen refueling stations. With about 28% greenhouse gas emissions from the transportation sector, a green alternative is the need of the hour. We are hence going to discuss an integrated electric vehicle and fuel cell electric vehicle charging station powered by hydrogen produced from solar PV. This study has been restricted to application in California due to the market and technological restrictions. Going further, we will first be discussing the necessity of this alternative technology by comparing with the dominant process employed in the industry for the production of hydrogen, steam methane reforming process. Solar hydrogen refueling stations is a strong contender for carbon neutral sustainable green technology. With a fair share of its pros and cons, the study of feasibility of this technology would be worth exploring.
To perform a technical analysis of our system, we need to do a market analysis of the FCEV and EV markets in California to define the demand of hydrogen. The projected number of FCEV and EV cars by 2025 is 17,500 and 1.45 million respectively. This clearly shows that our market is limited by FCEV market. We also assume that our client company is one of the leading companies in the field, such as Shell, with a market share of 13%. Through technical calculations, we conclude the daily demand for Shell's FCEV and EV market as 44.6 kilograms of hydrogen per station. From the demand of hydrogen, we size all our major components such as electrolyzer, PV, fuel cell, and storage, taking into account the respective efficiencies of 67, 20, and 70%. DNI data was used to get this hydrogen production from a supply point of view to size the storage. The solar to fuel efficiency is computed as 12%.
One non-trivial part of the technical analysis was the amount of hydrogen storage to purchase. Because the amount of hydrogen storage required depends on both generation and consumption rate, we needed to balance hydrogen sold over the course of a day to hydrogen generated based on photovoltaic power rating. We modeled hydrogen sold based on the traffic to a specific gas station in Santa Monica, and then matched our PV power required to this amount of consumed hydrogen. This allowed us to plot the total stored hydrogen over the course of a year, and the maximum value of this plot gave us the necessary hydrogen storage capacity.
For the components other than the hydrogen storage, we were able to do simple demand-side calculations to cost all the components using commercially available data, giving us a total capital cost of $88 million. The total lifecycle cost ignores tax and inflation, but considers installation and operation and maintenance cost, and the variable cost of water was also included in the total lifecycle cost, which came out to $103 million. We used this total lifecycle cost and a discounted revenue with a rate of 5% to perform a techno-economic analysis. You can see that this isn't a very good investment. At the end of the project's lifetime of 20 years, the net present value is negative $24 million. Projecting the revenue and total costs out further, we get a payback time of 40 years, which is double the project lifetime.
Adding further to the previous note by Karthik, this technology is compared to the prominent hydrogen energy production techniques like steam methane reforming, gasoline generators, and grid electricity. The most expensive current technology is SMR, which is about half the levelized cost of energy of hydrogen refueling station.
We also performed a number of sensitivity analysis. One important parameter that affects our performance is the amount of hydrogen production per station. On increasing it from 45 kilograms per day to 2285 kilograms per day, the LCOE drops to 28 cents per kilowatt hour and the payback period drops to 12 years. This extremely high value of hydrogen production is based on lowering capital cost components as per economies of scale.
The main conclusion we should draw from this is that, in its current form, solar hydrogen refueling stations at both low and high capacities aren't feasible. Low capacity hydrogen generation yields a payback time of 40 years, which is double the intended lifetime of the system, and high capacity generation yields a payback time of 12 years, which is still more expensive than all of the other competitors. Thank you.